Okay, so on our warm-up today, what we have angles that are outside the circle that are formed by secants, and on number 2 we have a secant and a tangent. So when the angle is outside, it's half the difference of the intercepted arcs. So this arc is 170, this arc is 52, so half the difference in the intercepted arcs tells us that this angle here is 59 degrees. Where's the 9? There we go. All right, well, these two angles are vertical angles, so x would also be 59 degrees. Any questions about number 1? All right, number 2, our angle, they actually gave it to us, 61. So 61 is equal to half the difference of big arc minus little arc. So we're 55 minus x. So I multiply by 2, I get 122 equals 155 minus x. Move x over here, the 122 over there, we get x equals 33. Okay, do these make sense?
Yep.
All right, so number 3, this time we have 2 tangents. Well, do you see that this arc and this one that's not marked make up the entire circle?
Yep.
Well, the entire circle is 360 degrees. So what are we missing right here? 94 degrees. So we would do 266 minus the 94 over 2. And that would give us x, which in this case is 86. All right, this one is very similar to 2. So we'd say 64 equals, this time it's x minus the 39 over 2. So there's 128 equals x minus 39. We'll add 39 to both sides, and we get 167 equals x. Any questions on 1, 2, 3, or 3? Okay. All right, let's go over your homework real quick. I'm going to come by, you're going to flip it. I'm going to try not to get nauseous while you're flipping. And we're going to talk about these. Okay, so these are the answers from the arithmetic. Okay, as you're getting them out and taking a look at them, what was big? Well, it was big trying to see if we could develop and remember the recursive formulas for an arithmetic sequence. When we graphed it, did we remember to not connect the dots because this is discrete?
Yes.
Okay? Now, what is not as big? This 10 and 11 is actually using the recursive and explicit formulas, but this sequence is not arithmetic, is it? If we look at it, it actually looks to be quadratic, doesn't it? So can we create a recursive and a explicit formula? Yes. But does it fall into what we're studying right now? No, not so much. So what we're looking at first is arithmetic. Any questions on these 2 pages? And then I'll come by and check the second 2. Now on these, did you tie into the fact that your common difference here ends up being your slope? Okay? The common difference is the slope. Now, normally we have it times n minus 1, so this is good. And so when we plug in, we can get our first term pretty easy. Our first term is not going to be the same as the y-intercept, though, is it? Because with our first term, that would be 1 for our independent variable. With our y-intercept, our independent variable would be 0. So 0 doesn't usually exist in the actual sequence when we're talking about the number of terms. Generally, we say that that first term is your first term. Seldom do we define the first one as a 0 term. It's possible, but seldom. Okay, any questions about that arithmetic page? All right, geometric. And once again, this one should also be discrete, but we put a lot in there. Okay, so here's that formula that we were building up to. This is the one we used last year. That's the important geometric there. Okay, I'm just checking most of it done. Good. Most of it done. All right, good. I'm just looking for most of it today. Versus normal homework, I'm looking for all of it.
For once, that's going to take exactly 15 minutes, like you said.
I told you.
I put a timer on everything.
Thank you.
Yeah, I started going like, I don't know.
Most of it, good. Your exam was
I have no idea.
CRTE.
What?
I did. All right. Alright. You'll do well with most of it. Okay. So, hopefully that brought back to our brains some of the things we studied last year. Now, when we looked at arithmetic and geometric sequences, is all we looked at last year in accelerated coordinate algebra and analytic geometry. We did this right before Thanksgiving. So, some of you were in good math mode and some of you were ready to eat turkey. So, when we go back over it this year, let's fill in any gaps we might have from last year. If there's something you don't understand from the sequences, make sure you ask me. Okay. All right. Ooh. How many people got number 10, where you had to take the log? Right. Who got this? We got one? Just one?
I felt like it was.
Number 10.
I didn't think it was asking. Yeah, I didn't know. I put 18 U. That's the first one.
Huh? Just one?
Isn't it plus one? Because it's like log of
Time D for you.
over.
Oh no, I didn't do anything.
Oh, now she got it right.
I couldn't find it.
Are you gonna share? Would you not add one?
Oh, yeah.
I just want to say, I just want to buy
Say
this like
$10,000 on $7. Doesn't that mean you have to add 10,000? You have to be able to get 10,000 in 1 month. Like you have 20,000 in 1 for the next month. So it doesn't mean that I'm actually never getting. She's adding 4 every single month. That's how long until she gets 10,000.
Oh, I see. Yeah. Yeah, it's because hers would hit in half a month.
Would you on there? You just have log of 40,000 or log of 2 plus, right?
That should say +1.
All right.
Yeah. I'm actually kidding. You're right.
That sounds right. Wait, Miss Willoughby.
Huh?
Well, I don't know. I don't know if you're thinking the same thing I'm thinking. With the Ashley thing,
Yeah.
2,500.5 months. That's just how long until she saves 10,000 all, and not just do 1 month.
No, this is I am using a sequence formula here, so it's not actually adding them up. You have to use the summation formula to add them up. So this is in one particular month. She would make that much. And I'll talk to you about that in a minute.
I'm so confused.
Okay. We'll talk about that in a second. Okay. Oh, where's my phone? Where is it? Okay, go.
What?
No calculators. No electronics. Go.
1 plus 2 is 3. Oh boy.
Yes, 1 plus 2 is 3.
You just have to
So like,
1,000.
what? I'm confused with the question.
She said no how.
Don't just say yes or no. Actually find the sum. Yeah, because the question is a yes or no
That's
question.
perfect.
I get it. All right, you got 30 seconds left.
I haven't started.
Okay.
I'm not even gonna try.
Are we counting like?
20 seconds.
Okay, like 3.444 or something like that.
Wrong.
Are we counting those though? I mean, like the decimals.
No.
Just hold on.
No.
Oh, I feel like
10 seconds.
When the age
5,006.
All right, anybody get it? You can't use calculator. Why do we all have calculators?
One second.
Anybody?
I got infinity.
All right.
I got the 50.
So, when you pick your senior jersey nickname, none of you will be Goss. None. Okay?
Darn, Miss Willoughby, you
I know.
did that.
All right, so let's learn about Goss for a second, and I can tell the story, but so can this guy. He uses a funny accent. Oh, hold on, you can't hear.
Hello, I am Carl Friedrich Gauss. Not to exponentiate my own quadratic, but I am considered by many to be the greatest mathematician to have ever lived. I showed promise even from an early age. While attending primary school in the late 1780s, my teacher tried to occupy my unruly class by asking us to add the integers from 1 to 100. I completed this seemingly monumental task in a matter of seconds, much to the dismay of my teacher. So, how did I do it? Suppose we listed the numbers from 1 to 100. Underneath that, we list all the numbers from 100 down to 1, lining up with the numbers above. Once set up in this fashion, we see that each number on the first line added to the number below it on the second line gives us 101. 100 plus 1 equals 101. 99 plus 2 equals 101. 98 plus 3 equals 101, and so weiter. We have 100 such pairs of numbers. So the total of these two sets of numbers is 100 times 101. This, however, gives us twice the amount that we are looking for, since we have added two sets of integers from 1 to 100. So we simply divide the total by 2, yielding an answer of 5,050.
All right. So this tells the story of Gauss. All right, and we're not sure if this is a true story or just kind of like one of those wives' tales. But Gauss was a brilliant mathematician, and he was a child prodigy. So it wouldn't surprise me if this little tale that they tell is actually true. So what did he do? He was adding up all the numbers 1 to 100, similar to the assignment I gave you. Adding them all the way up till he got to 100, right? But then he noticed, if he did it backwards, and did from 100 down to
There's no way he invented this in a number of seconds. Yeah,
1,
definitely lied.
Oh, that makes sense.
and we did the sum of this, you see every time we get 101. 101. 101. All the way to 101. And if we did it from 1 to 100, how many times did we get 101? 100 times. We would get 101. But his teacher just asked him to add from 1 to 100. Not from 1 to 100 and from 100 back to 1. So he actually doubled the assignment. He did it twice. So what he did was he divided it by 2. So when you do 50 times 101, you have a 0. 5 times 1. 5 times 0. 5 times 1. 50, 50.
So you just take
I still don't get
half of the number.
Pretty cool, huh?
it. Will this be on the test?
Yes.
Oh, gosh. Oh.
Okay.
But
So,
you take half the amount of numbers in the sequence.
so let's not stick with just the 1 to 100. What if we were trying to add up any sequence of numbers?
Will we just
I
take the
know how
highest
to
number
do it.
add
Okay? What that gives us is what we call a series. A series is where we do a summation. We sum up a sequence. And the Greek symbol sigma is what we use for summation. So if you look at on websites, you might see this symbol because this means to add up. Yes, Ben?
So do you just take like half of the biggest number in the series and multiply it by the highest number plus the lowest number to get how much is in how much?
That is sort of what we do, yeah. You said it pretty much correctly, yes. Okay, so summation is where you find the sum of the terms. That's what summation is, where we sum up the terms. Okay, so let's think about the arithmetic. An arithmetic sequence. And when we looked at our learning task yesterday, it took us back to the formula to find any term, the nth term of an arithmetic sequence. Does anybody remember that formula? A sub 1 plus n minus 1 times d. Okay, so that's the formula we used last year. That's when we were just trying to find a term in the sequence, right? Well, now we want to learn how to add them up. Okay, and what I'm going to say for you guys right now is I want you to watch what I'm doing. And if you want to copy this down later on, you can. But I don't want you to spend all your time copying and miss the good part. Okay, so let's go with Gauss's idea here. And let's see if we can develop a formula that will give us the sum of an arithmetic sequence. If we found the summation. All right, the first term in an arithmetic sequence we call a sub 1, don't we? Does that make sense? First term. All right, now I'm going to add to that the second term. Now, to find the second term, can I take the first term and add a common difference? Does that give me the second term?
Yes.
Yes. Okay. Now, let's represent the third term. Can I take the first term and add 2 common differences to get to the third? Yeah. And then the fourth term, what do you guys think the fourth will be? Yeah. A sub 1 plus 3d. Okay, so we kind of continue this idea until we get to the last term. And normally we call the last term the nth term. Okay, how can we describe the last term? Well, isn't that just this formula?
Yep.
Doesn't that find the nth term? So I'm going to represent the last term as the first term plus n minus 1 common differences. And does that make sense? Is 3 1 less than 4? Is 2 1 less than 3? And 1 is 1 less than 2? Okay, good. So if we were Gauss, now we would start working the other way. So we would take this first term and add it here to the last one. And then we would take the last one and add it over here to the first one. Okay, so if this was n minus 1, could I say this one is n minus 2? And could I say this one is n minus 3? And this one would be n minus 4. All right. The ends are actually the easiest. We'll talk about the middle in just a second. So let's do it. Let's add these two together. So let's add the last one and the first one together. We have an a sub 1 and an a sub 1. How many a sub 1s is that? 2. 2 of them. Plus an n minus 1 times d. Do we get the same thing over here? An a sub 1 plus an a sub 1 is 2 a sub 1s plus an n minus 1 times d. Now this is a little harder to see, but I'm going to kind of finagle it a little bit. If I were to distribute right here, do you see I get dn minus 2d? And if I do a minus 2 and a positive 1, is that dn minus 1d? And then if I factor that d back out, do you see if I factor the d back out, it leaves me n minus 1 times d? Guess what's going to happen every time? I'm going to get 2a sub 1 plus n minus 1 times d. I'm going to get 2a sub 1s plus an n minus 1 times d. Well, how many times do I get that? How many times? This is 1, 2, 3, 4, all the way to the n times. So if we take Gauss's idea, we would do n divided by 2 times 2a sub 1 plus n minus 1 times d. This is one of our formulas to find the summation. Okay, write down the formula. Okay, now this formula doesn't sound as neat as what Ben was saying a minute ago. So let's kind of manipulate this formula a little bit. I'm going to break this formula apart. We just added these two a's. I'm going to separate them. Do you see all I did was break that back up? Now, I chose to separate it on purpose because what is this? Do you see it matches? This is a sub n. So my other formula, this is the one I like to use because this is the one I can remember. It's the first term plus the last term divided by 2 times the number of terms. This is my favorite formula right here. Willoughby fave. My brain doesn't want to memorize this one. I don't know why. But I'm good with this one. Okay, so this is what Ben said. Do I just take the first one and add the last one to it and divide that by 2 and then multiply by how many terms there are? Yeah, that's exactly what you do. And that's our shortcut to finding the sum. Much nicer. So, this was our question for math team this morning. The question was, what we're going to do is we're going to add all the, you can't even tell what that word was, the multiples of 3 that exist between 1 and 2013. And then after we add all those up, if we divide by 100, what's the remainder? That was our math team question this morning. So now, could we do this? Can we find all the multiples of 3? So what I started doing is that I started writing. I went 3, 6, 9. Ooh, that's an arithmetic sequence. And the first term is 3. And my last term is 2013. How do I know that 2013 is a multiple of 3? Because when you add up all the digits, they are divisible by 3. When we add this up, it's 6, and 6 divides by 3, so we know this does. Okay, so I'm halfway there. N over 2, first plus last. Well, how can I figure out which term 2013 is? What is its position in line in that sequence? Well, can't we just divide it by 3 and figure out where it would lie? Okay, so what was it? 671. Okay, so this is what we do. 671. Okay, this was on a no calculator part of a math test, a ciphering, so you're supposed to be able to do it in a minute or less. So this part, if we thought about it, we could get here in what, 5 or 6 seconds? Okay, so now we have to add these two. And then I'm going to divide that number by 2 because it's even. And I know my remainder when I divide by 100 would just be the 10s in the 1s place. Right?
Right.
That's your remainder when you divide by 100. the tens in the ones place. So when I'm multiplying, I really only care about the tens in the ones place. So I'm going to do 8 times these two, and that ought to be good enough. So 8 times 1 is 8. 8 times 7 is 56. So my answer is 68. That'll be the remainder. Who's ready to join math team?
I didn't get that last part.
I'm good.
Why is it 68? Why?
Because if you just punch this in your calculator. 671 times 1,008. Sure. It ends up being the decimal part.
Yep.
Good. All right. So that was one of our slicing questions we practiced this morning. All right. Today's notes. Here they are. You have a note sheet. We'll fill these in together. So Doug, I know you're watching this tonight. Sad that you missed math. Everybody shout out to Doug.
There's nothing.
All right. Who else is missing today?
All the boys you have.
Amaris is out. Everybody shout out to Amaris.
They don't watch the video.
Don't miss our shout outs.
Go ahead and call it. Doug's not gonna watch this.
If we tell him we shout it out to him, he will.
All right. All right.
We're only here until like 9:15.
Okay, so this was our explicit formula for an arithmetic sequence. A sub n equals a sub 1 plus n minus 1 times d. I usually write the d at the end. It doesn't matter. Multiplication, you can switch it up. All right, series formula, the one I like. My fave is n divided by 2. The first term plus the last term. Now the other one also works, and sometimes it's quite handy. So we'll look at both today. Okay, how do we know we have an arithmetic sequence? An arithmetic sequence. That's when we have a common difference. And if you're looking at a sequence of numbers, what you'll notice is that we're adding the same number or subtracting, you can think of it either way, the same amount every time to go from term to term. First is geometric. Instead of adding, what are we doing to go from term to term? We're multiplying. So it has a common ratio because we can take any term and divide it by the term before it and find that multiple. So here we are multiplying by the same amount over and over again. Okay, and when we look at the arithmetic formula, what you noticed on your task was this one turns out to be linear. And when we look at our geometric, according to our task, this one turns out to be exponential. Because repeated addition can be written in a linear format, but repeated multiplication ends up being written with an exponent, right? Okay. All right. Now, the domain of the sequence, that's our input. We think of that as the position of the term. First place, second place, third term, fourth term, fifth term. There are counting numbers. What set of numbers is a set of counting numbers?
Whole.
Very close. Whole includes 0, and we normally don't. Normally, natural. So generally, our domain of a sequence is just a set of natural numbers. Now the range, the output, ends up being just those terms that are in the sequence. Okay. Now, with a sum, which is what we're adding this year, the sum is the new part. A sum of a sequence is called a series. And we have two types of series. We have finite. I'll give you a very fancy math definition. That means it ends. A finite sequence. And then we have an infinite. Can you guys give me a very fancy?
Goes on
adjective?
forever.
It does. Okay, it does not end.
Not.
Goes on forever. That's right.
Today.
That's your definition.
Today
This
has to be
class.
Today is really long.
All right.
Like, God, it's not even over yet. What is this?
All right. So, if can represent two things. It's either the position of a term in a sequence, or it's the number of terms in a sequence. So if we look at these three, can we identify it as arithmetic, geometric, or neither maybe? Maybe it's not either. Okay, what about the first one? The first 5 terms in the sequence. So if we plugged in a 1, we get out a 7. If we plug in a 2, we get out a 10. If we plug in a 3, we get out 13. If we plug in 4, we get out 16. It's definitely which one? Arithmetic. And if we look at it, is it described in a linear fashion? Yes. That's almost y equals mx plus b mode, isn't it?
Why is it like an exponential sequence and a linear sequence? Like, that would make so much more sense.
Well, repeated addition ends up being multiplication. So it's arithmetic because we're repeating that addition. I'm not sure about the other one.
Yeah.
I should probably research that. Now this one, if I plug in 1, I get out -2. If I plug in 2, I get out 1. If I plug in 3, I get out 6. If I plug in 4, I get out 13. Up by 3, up by 5, up by 7. No, that's not constant. I'm not multiplying by the same thing. So this is a neither. Obviously, we're looking at it, and it has a quadratic in it. So if we were going to model this quadratic is a good way to go. But arithmetic ends up being linear. Geometric ends up being exponential. Now, normally this is to the n-1, so this n throws me off a little bit here. Because usually when it's to the n-1, this is my first term, which is not true for this one, because they have it raised to the n. So that's a little different for me. So if we plug in 1, we get out 6. If we plug in 2, we get out 9 times 2 is 18. If we plug in 3, we get 27 times 2 is 54.
No.
Do you see it's multiplying by 3? Times 3 times 3? That is my base that's being raised to the exponent. That is my multiplier when I call it a times b to the x mode. This is my multiplier. And so it's a common multiple, common ratio, geometric.
I'm confused. How did you get, is the 2 like multiplying by the 3n?
Yeah, it's 2 times 3 to the n. And of course we follow PEMDAS, which says we have to raise it to this power before we multiply.
So n was 2.
Yep. 3 squared is 9. And 9 times 2 is 18.
Neither metric.
Oh, that's awesome! Ooh, that could be a new math term. Neither metric. I love it. I'm going to write a paper about that and get it published, so I'll have a new term. Remember, neither metric. Neath metric? Neath metric. I like it. I like it.
It was the other came
I
about.
think that was
All right.
I feel like it needs an A.
Okay. It was just neath metric.
You just wrote needs that.
All right, there we go. I like that too. All right, oh, that's so good. Okay, so when we look at these, all of these types of examples fall into arithmetic or geometric. The sum of this. Do you see? This is a series. We don't have commas here. What do we have? Pluses. We're adding it up. It's a sum. It's arithmetic though. Do you see it increases by 2, increases by 2? Okay, so this is new. We didn't do that one last year. Now this one, down by 2, down by 2. And they're just asking us for the 98th term. That's old. We did that last year. That's just where we plug it into that one formula. This is not a series. This is just a sequence. Write in the explicit formula. Old. Find the 19th term. Old. How many terms are there in the sequence? Old. If the 6th term is this and this term is that, what is 9? Old. All of this we did last year. That's so last year.
How do you do number 6 again?
I'm going to run out of time if I show you right now, but I can show you.
Okay.
All right, number 7 is new because this says find the sum. Number 8 is new because we're finding the total number of seats in this amphitheater. Okay, so 1, 7, and 8 are the types of problems we'll be doing now. We're going to revisit some of this old so we don't forget it. But 1, 7, and 8, that's our new. So let's look at number 1. If it asks to add up from 1 to 21, this is not hard. If you're taking the SAT and the formula slips out of your brain, you can actually punch in 1 plus 3 plus 5 plus 21 and get the answer, couldn't you?
That's probably
Okay?
what I would do.
But usually they're going to give us like a huge number here, which makes us go back and remember this. So I know the first term is 1. I know the last term is 21. What I'm missing, to use my happy formula right here, is n. That's what I don't know. And when I'm missing something like that, I have to go back to last year's formula. To find any term in a sequence, it's the first one plus n minus 1 times the common difference. So 21 is my final term. 1 was my first term. I don't know n. What is the common difference right here, though, guys? 2. And then algebraically, I'll just solve this. Right, Eric? Yes. So I'll subtract 1. And I'm probably not showing all these steps, but I'm just doing this for you. Divide by 2. Add 1. So now we know that 21 is the 11th term. So now I know n is 11. Now I've got it all. I've got n, I've got the first term, and I've got the last term. So the sum of the first 11 terms is 11 divided by 2, 1 plus 21. The sum of the first 11 terms is half of 22 is 11, and 11 times 11 is 121. Okay, so what I did, folks, was 1 plus 21 is 22. Half of 22 is 11. 11 times 11 is 121. Number 7. 3, 8, 13, 18. What is the common difference? 5. They gave us the first term is 3. We know the common difference is 5. They asked us to find the first 20 terms. Now, they didn't give us the last term. So I could use that second formula that is n divided by 2. 2 times the first term plus n minus 1 times d. So the sum of the first 20 terms is 20 divided by 2. 2 times the first term plus 20 minus 1 times 5. All right, so this is 6 plus 100 minus 5. And 100 minus 5 is 95. So 6 plus 95 is 101 times 10 is 1010. All right. Are you ready? They're very ready. I will allow you to use your calculator, but you may not use your phones. Find the sum of the numbers 1 to 1024. Go! 30 seconds remain. And time is up. Okay, if you have written down on your paper, 524,800. Who's got it? Who's got it? Come get a piece of candy. All right, backside your homework. One piece, no cheating. You only get candy if it's right. Honesty policy.